All right, we are recording now. Yeah, so if you have a symmetric matrix, all its eigenvalues are real. And if you look at eigenvectors corresponding to different distinct eigenvalues, they're orthogonal. And if you have an eigenvalue of multiplicity k, you can find k orthogonal eigenvectors. And the components of these eigenvectors can be, without loss of generality, be taken to be real valued, okay? And you can make them orthonormal by normalizing. So the conclusion is that for a real symmetric matrix A, its eigenvalues are real, and we can find orthonormal eigenvectors, which each of which belongs to Rn, such that if you look at the inner product, it'll be 1 if I equal to j, and 0 otherwise. Okay, so that's where we were at last time, and then we're ready to start today's lecture now. So based on that result that we just described, okay, we can actually show that a symmetric matrix with real entries can be expanded out. Okay, this is called the eigen or spectral decomposition or eigen decomposition of a matrix. You can write it as a sum of lambda I ui transpose. Okay, summed over all the indices I. Okay, and these, of course, these eigenvalues are real. We just showed that last time. And these eigenvectors belong to Rn and they're orthonormal. So you can write this as a product of three matrices by stacking all the eigenvectors into a matrix like this. U1, the first column is U1, second column is U2, and so on. And you get this matrix U. And this matrix U is an interesting matrix. If you look at the transpose of U, okay, the transpose of U is going to look like, the U transpose is going to look like, it'll have rows, which are U1 transpose, U up to UN transpose. So if you multiply U transpose with U, okay, what you get is, because they're orthonormal, the product of these two matrices, you can immediately see that has to be the identity matrix. Okay, and that means that the transpose of U is also the inverse of U. And such a matrix is called an orthogonal matrix. Okay, so basically you can write A as the product of U and a diagonal matrix containing the eigenvalues and U transpose. Okay, now how do you show this? It's actually very straightforward. You just make use of the relationship ui equals lambda I ui, I equal to 1 to n, and then you basically stack all these vectors on the right hand side here. You can do this at home. Stack all these vectors on the right hand side here, and then you'll have a matrix. You'll see that the right hand side will be a product of two matrices. So you basically show that A times U, the matrix U, is lambda times U transpose. That's what you're going to end up showing. It's U times lambda, okay? And then because the inverse of U is the same as U transpose, by multiplying by U transpose on the left-hand side, you get rid of the U here, and then you end up with this on the right-hand side. So that's pretty easy to show. So you can do that at home. Okay, so any questions? Again, if you have questions, just unmute. Okay, all right. So now let's actually give an important result, which we'll have occasion to use several times in this course, which is that if you look at a matrix A that's symmetric, then the let's see, okay. if I look at X transpose AX for X being any real vector in Rn, this X transpose AX is less than or equal to the maximum, the largest eigenvalue times the norm of X squared, and bigger than or equal to lambda min times the norm of X squared. Okay. So how do you show a result like this? So what you do is you basically exploit the fact that the UIs are orthonormal and they form a basis for Rn. Okay, so since they form a basis for Rn, we know that we can write this as any X can be written as in terms of the bases with coefficients, say alpha I, like that. So for some alpha i's that are in the real one. Okay, so now let's use this fact and look at what X transpose AX becomes. So X transpose AX can be written as summation I equal to 1 to n and then I'll repeat that thing there with the different index here, just to make sure I don't confuse the indices, right? And so this just becomes a double summation. Alpha I, alpha j, and ui transpose a uj. Okay. Now, if you look at this thing here, by the definition of an eigenvector, so this is equal to lambda j times uj. But the ui and the ui's are orthonormal. So if I look at ui transpose uj for I not equal to j, I get 0. So this double sum basically will collapse down to just a single sum, right? For I equal to j. So I'll just get summation I equal to 1 to n alpha I squared times lambda I. Okay. All right. So that's what X transpose AX is. So, but if you look at that summation, the smallest value, it'll be lower bounded rather. It'll be lower bounded by if I replace lambda I by lambda min. So I can find a lower bound for the summation as lambda min times summation I equal to 1 to n alpha I squared, and it's upper bounded by lambda max alpha I squared. But what is this summation of alpha I squared? Well, from the result statement, it should be the norm of X squared, right? And why, you know, what this result is called from your undergraduate, maybe linear systems class where you did things like Fourier transforms. Anyone? Parseval's theorem, that's right. So energy is preserved when you transform, right? So it's basically Parseval's theorem. That's what you might remember from your linear systems class. So equality on the left-hand side, when is that achieved? Anyone? So these bounds are tight. They're achieved for certain values of X. And what value of X achieves the left-hand side? Anyone? Just unmute and speak up.
Wouldn't it be the eigenvector corresponding to lambda min?
Very good. Yeah, it's the eigenvector corresponding to lambda min. If X is equal to the eigenvector for lambda min. And similarly, the right-hand side is achieved if X is the eigenvector for lambda max. Okay. All right. So again, we'll use this result in many places. In fact, we'll probably use it in today's lecture too. So you keep that in mind for the future. All right. Some other things about matrices that are useful to know. So the trace of a matrix. The trace of a matrix is the sum of its diagonal elements, right? So trace of A is summation AKK. But the trace has an important invariance property, which actually turns out to be very useful in many calculations, right? Even when things are stochastic. So you might, if you take a course like ECE 561 or even ECE 534, you might see this property of the trace being used in interesting ways. So what's this property of the trace? What it says is that if I multiply three matrices, and they have to have the right dimensions so that I can multiply them. So A is m by n, B is n by k, C is k by m. Okay. So if I take the product of these three matrices, what I end up with is an m by m matrix. Okay. Now the invariance property says that the trace of this m by m matrix is the same as the trace of, but you can basically bring the C from the right hand side and put it in front. So it's kind of a rotation invariance. Okay, it's the same as trace of CAB, but CAB is actually a k by k matrix. And this is the same as the trace of bringing B now, so BCA, which is a BCA will be an n by n matrix. So all these three matrices have the same trace. Okay, and it's very easy to prove just from the definition of the trace, because you can actually write this down. Write the trace in terms of you first write down the product of the matrices as a double sum, and then you manipulate the terms in the double sum, and it easily follows. Okay, but it's a very powerful result that can be exploited in interesting ways. The other thing about traces and determinants is that I can write the trace and determinants in terms of the eigenvalues of the matrix. Actually, this holds even for non-symmetric matrices, but for symmetric matrices, it's much easier to prove. Okay, if you want to see the more general result, you could probably search on Wikipedia or some place like that to find it. Well, let's actually look at it for the special case of symmetric matrix. For a symmetric matrix, we already showed that I can write it as U lambda U transpose, where U is this orthogonal matrix, right? And since U transpose and U will have the same determinant, and since U transpose U is equal to I, each of the U's actually has determinant equal to 1. So we're going to exploit that. So determinant of A is the same as determinant of U lambda U transpose. And we saw that this can be written as a product of the determinant. So it's determinant of U times determinant of lambda times determinant of U transpose. Okay. And then each of these is equal to 1. And so you just get determinant of lambda. And it's a diagonal matrix, so the determinant is just a product of the diagonal elements. So that's how you get the product of lambda i's. Okay. Similarly, the trace is the trace of U transpose, and here's where we're going to use the trace invariance property. So this is the same as trace of lambda U transpose U, but U transpose U is the identity matrix. So this is just trace of lambda, which is a diagonal matrix, so you get the sum of the lambda I, right? So that's how you show these properties. So next we define something called positive semi-definite and positive definite matrices. And again, we will see these appearing throughout the course. Okay. So what's a positive definite matrix? A symmetric matrix is said to be positive definite. Again, the definition really only makes sense for symmetric matrices. Okay, so a symmetric matrix is said to be positive semi-definite, or PSD, if I look at X transpose AX, this has to be positive, or no, non-negative, sorry, for all X belonging to Rn. And the notation for this is that we write this as A with a little squiggly, like kind of a curved greater than or equal to sign. Okay. Sometimes people just use a greater than or equal to sign, but I like to make that slight distinction for matrices. So this greater than or equal to sign here is slightly different from the one here, even though with my handwriting it probably doesn't look that different. Okay, so so that's positive semi-definite matrix. What about a positive definite matrix? A positive definite matrix, basically this inequality has to be strict. Okay, but of course the inequality, it would equal 0 when X is 0. So this is strict only for all X not equal to 0 that belong to Rn. And the notation for positive definite matrix is that this. And if you look at negative semi-definite and negative definite matrices, all you do is basically reverse the inequalities. And that's a definition for those. Okay. Any questions? Yeah. No? Okay. Think a little bit, at home, think a little bit of why this definition doesn't make sense for a matrix that's not symmetric. Okay. All right. So what are some ways to figure out if a matrix is positive definite or positive semi-definite? Well, you could try out every X and prove, or actually sometimes you can actually prove that X transpose AX is either strictly greater than 0 for X not equal to 0, or greater than or equal to 0 for all X, and that's how you can establish that it's positive definite or positive semi-definite. But there are other tests which are more convenient. Okay, the one test for positive definiteness is that all eigenvalues of matrix are positive. So we already know that it's for a symmetric matrix they are real valued, but if it's positive definite, its eigenvalues are guaranteed to be greater than 0. Okay. The other test, which is actually more convenient in practice, is that if you look at all the leading principal minors, so what are principal minors, first of all? Anyone know what the definition of a principal minor is? You should have seen this in linear algebra. No? Well, a principal minor is a matrix obtained when I delete a row of the matrix, okay, and delete the corresponding column with the same index, right? So if I, for example, to create a principal minor, I could delete the first row and the first column, and this is the matrix I would obtain. Or I could delete the second row and second column, and then I get 1, 0, 0, 2, okay? Or say the third row and third column, I get 1, 0, 0, 2, this one. Or I could delete more than one, so I could delete some subset of rows and columns with the same index. So I could say, for example, delete the first row and the second row and the first column and second column, and then I'm left with just this 2 as a possible principal minor. So if you can check the principal minors basically the principal minors actually are the matrices, the determinants of those matrices. So that's actually the definition of principal minor, not just the matrix itself, but its determinant. So if you can just check that all the leading principal minors of A are positive, then you can conclude that the matrix is positive definite. Okay. So, for example, the leading principal minors, to get the leading principal minors, you basically keep the first k rows and first k columns and delete the rest. Okay, and you do that for every k. For example, the leading principal minors in this case would be the matrix with 1 here, this 2 by 2 matrix, and the whole matrix A. Okay. All right. So now let's see whether we can apply these tests to figure out whether this is positive definite or not. Well, we actually found the eigenvalues of this in the last lecture. You might remember that it was lambda 1 equal to 4 and lambda 2 equal to lambda 3 equal to 1, right? Was that what we had? Anyway, they're positive basically. That's all that. I think we saw this one. 3. It was 3. Okay, not 4. It should have been 3, I guess. Anyway, so we basically this means that A is positive definite from that property. But you can also look at the principal minors. So principal minors, you look at the determinant of the first principal minor, which is just 1, and then you take the determinant 1, 0, 0, 2, and that's 2, which is also positive. And the determinant of the whole matrix, which was equal to 5, I think, which we saw last time. It's actually easy to see here. It was 1 times 4, 5, which is positive, which implies that A is a positive definite matrix. Okay. All right. So that's one thing. What about for positive semi-definiteness? So here it gets a little more complicated. The eigenvalue test is still almost the same. You just check to make sure the eigenvalues are all non-negative, and then you can conclude that. But if you want to avoid computing eigenvalues with the matrix, especially with the large matrix, then you can test the principal minors of the matrix, but you need all principal minors to be non-negative. So it's not enough for the leading ones to be non-negative. Okay, again, this is something you should have seen in your in 415. So it's not enough to check leading. You need to check all. And let's see why. And let's look at an example. So if the first example is a 2 by 2 matrix, which for which lambda 1, it's easy to show actually lambda 1 equal to 1, lambda 2 equals 0. So this is positive semi-definite, right? Lambda. But you can also do the principal minor test. And so the principal minor in this case has both the principal minors are 0, right? And so they're non-negative. And so you get you have to check all of them. So the first principal minor here, this one is 0, this one is 0, but then you have to also check this guy, but this one is positive, right? 1. So the principal minor test says that it's a PST matrix. Okay. What about this matrix here? So if you can easily show in this case that lambda 1 equals 0 and lambda 2 is minus 1. Okay. So we know that this is not PST, right? But if we just look at the leading principal minors, so this guy and this guy, both the leading principal minors are 0, so they're non-negative. But if you include all principal minors, then you have to include this guy, which is negative. And so that's how you conclude that it's not BSD. Okay? Any questions about this? Okay. All right, so now let's talk about matrix norms. This is probably the last topic, review topic. So matrix norm. So we define a vector norm and the Euclidean norm, which is mostly what we deal with, which is the square root of x transpose x, right? Or square root of the sum of the squares of the components of x. But if you have any vector norm in Rn, you can actually produce what's called an induced norm on matrices, on n by n matrices. Okay, and the induced norm on the n by n matrix is given by this. What you do is you basically look at a times x, and this is a vector now. So and you take its vector norm, and you maximize this over all x in R2 such that norm of x is 1. So you look at all normalized vectors with norm 1 and compute the norm of a times x and then maximize over that. Okay. So this set here, what kind of set is this set? The set of all x's such that the norm of x is 1.
Circle?
Yeah. It's a compact set, right? Right? It's a compact set. Okay. And so this max is going to be achieved. Okay. All right. And I can also think of this, write this max as in the following way, and sometimes it's more convenient to think about it this way. So I can take the max not of normalized x's, but any x that's non-zero, and take the norm, norm of ax and divide it by x. So can you see why this is why this is the same thing? Okay, maybe it's something that you should think about at home. So it's not hard to see that this maximization over all x is the same as this maximization of for the normalized x, because I'm dividing by x here, and that's how I take care of. That's how I end up normalizing x. Okay.
I'm sorry, Professor. Should the r square be rn instead?
Oh, yeah, sorry. That r squared should be rn. Yeah, absolutely. Yeah. Very good. All right. So now we'll define another quantity related to a matrix A. This is the spectral radius of a matrix. So the spectral radius of a matrix is the max. By the way, even though I may not specifically mention it, we are only dealing with symmetric matrices, okay, in this course. So make that assumption throughout. Okay. So although some of the results may hold even for where the matrix is not symmetric, but we don't care about that. So spectral radius is of a matrix is the maximum value for the maximum absolute value for the eigenvalue. So it's maximum of the magnitude of the eigenvalue. Okay. Interestingly, there's a relationship between the spectral radius and the matrix norm. Okay, and that's this result here. This result says that if I look at the spectral radius, it's always less than or equal to the matrix norm. So let's actually quickly prove this. Right? So let lambda be an eigenvalue of A and U be the corresponding unit eigenvector. Okay. Then I can write A times U, the norm of A times U, is the same as the norm of lambda times U, right? Which is the magnitude of lambda times the norm of U. Okay, but the norm of U is 1, so this is just the magnitude of lambda. Right. So now let's look at A times the norm of A times U and compare it with the left-hand side here that I have. So here I'm taking all unit norm vectors and taking the max of AX, right? So a specific choice of that X would be this U, which is also normalized to have unit norm. So the specific choice should be smaller than the maximum. So this should hold. But that we just showed was equal to magnitude of lambda. And this is true for every eigenvalue. Okay. So that means that the left-hand side is actually the definition of the norm of the matrix, or the induced norm of the matrix. So the induced norm of the matrix must be greater than the maximum over the eigenvalues. So which is the row away. Okay. Oh yeah, I should have. No, maybe I was a little quick in saying this. Actually, all these definitions so far hold for any matrix A, and this result also just holds for any matrix A. Okay, and if the matrix A had complex eigenvalues, you still take the magnitude of the complex value there. So it actually so far these results hold for any A. For symmetric A, which is what we'll mostly be dealing with in this course, we have that the matrix norm is actually the same as the spectral radius. So sometimes the matrix norm for a symmetric A is also called the spectral norm, okay, because it's related to the spectral radius. Okay, so how do we show that? So symmetric A, which is what we'll be dealing with mostly in this course. How do we show that? We just showed that the norm of A is greater than row A, right, for any matrix A. But for symmetric A, we now need to show the opposite inequality. So we need to show that A is less than row of A, or row of A is bigger than the norm of A. Okay, so we need to show row of A is bigger than. And then we'll be done. Okay, that will mean that it has to be equal. Okay, so how do you do this? So you take any X belonging to Rn, right? Again, like we did in the previous proof, we can write X, expand X in terms of the orthonormal. Like since we now know for symmetric matrices, we know that we can find these UIs that form are orthonormal and form a basis for Rn. And so we can write it this way. And now if we look at A times X squared, I can write that as the norm of the summation of alpha I A UI squared, which is equal to the norm of, I can replace A times ui by lambda I times ui. Right? And now what do? So if I exploit the orthonormal property of the UIs. And so if I look at the summation of these guys, I'll get the summation of this, just the square, basically. Write that as a double sum first, and then only the diagonal terms remain. So you'll end up getting a single sum with the squares of the alpha I and lambda I there. Okay. And this is less than or equal to, I'll put the lambda max there. If I replace the lambda I by lambda max, I get the spectral norm, actually the square of the spectral norm because I have the square of lambda I here. So this is less than or equal to summation I equal to 1 to n alpha I squared times the spectral norm squared. But this is just by Parseval's theorem, we just saw that this should be norm of x squared, right? So what did we show? So what do you have to do now? You can divide, say, assuming that x is not equal to 0, you can divide this right-hand side and left-hand side by norm of x squared, and then take the square root, and then you end up using this definition. Using this definition, you end up with the matrix norm being less than rho of A. Another way to do it is just choose x, just make x a unit norm vector, and then this relationship will hold for all x that have unit norm. In that case, this will be 1, and then you'll just conclude that the max over all unit norm ax squared is less than rho squared, from which you can conclude that the matrix norm is less than rho of A. Okay, so basically for symmetric matrices, the spectral radius is the same as the matrix norm, induced matrix norm, and so that's why for symmetric matrices, this induced norm is sometimes called the spectral norm. Right? Any questions? All right. If you don't have any questions, we're going to move on to another topic. So maybe we can take a couple minutes break, and then we'll get to some examples of optimization problems. Okay. All right. So 2 minutes. So we're at 11:44. 11:46. We can reconvene. Unless you have a question.
Professor, I have a question regarding last slide.
Yeah.
So for the last equation, can you explain a little why the inequality holds?
Yeah. Oh, you want me to explain why that inequality holds?
Yeah.
Oh, yeah. That's because the lambda I is the maximum value of lambda I. Sorry. The maximum value that lambda I is defined to be the spectral radius, right?
Mm-hmm.
And so if I replace this by the maximum value, it goes outside the summation and becomes a spectral radius squared. And then all I'm left with inside is just alpha I squared.
But it gets summed n times.
No. The alpha I squared, the summation applies to this. So I just take the lambda I squared outside the summation.
Oh, okay. I see.
Yeah.
Right. Yeah. Thank you.
Any other questions?
Can you repeat again? How do you like start from the last step to the conclusion?
Oh, last step to the conclusion. There are two ways to do it. One is you can take the norm, you can take the max of this over all x's such that norm x equal to 1. In which case the right-hand side would be, this alpha I squared will be 1. And you conclude that this thing is less than rho a squared. In which case you get that the max of ax is less than equal to rho a.
Mm-hmm.
Okay. The other way to do it is just to have what we were saying. You could just from this you can conclude that ax is less than or equal to x rho a, and then you divide by, for all x not equal to 0, I'll divide by this, you get that, and then you take the max over x. And this is the matrix norm.
Okay.
So there are two ways to do it.
Thank you.
Right. Okay, so, well, we didn't take our break yet, so let's take it now. So it's 11:47, 11:49, we can reconvene. Okay, so get yourself some tea or stretch, whatever you need to do. All right. Okay, welcome back. Chelsea, your video is upside down. It's interesting. Is that on purpose? Okay, so let's let's talk about some examples of optimization problems. So now that we have actually set up the notation and the background, I thought it would be a good time. These problem formulations wouldn't have made sense without first introducing some of the basic math notation. So let's talk about an interesting application, first application of optimization. Okay, and we'll revisit these things throughout the course. So, as I teach some theory material, at some point I would take a break and then look at an interesting application and maybe focus a lecture on that, and then move on to the next piece of theory material. Okay, so an example, a very interesting use of optimization is in the context of least squares or linear regression. Okay, it can be thought of as a machine learning application. Okay, so you have a bunch of data. Okay, so X and the data are XI, YI pairs. Okay, in this case, X and Y, just for illustration, X and Y are both scalars, but think of X being something very high dimensional, Y might be a scalar. Okay, and you want to form a linear fit to the data. So you want a linear relationship between the Y and the X. Okay, so basically, you want to find a linear relationship of the form yi equals A transpose xi plus b. So this xi could be a high dimensional vector belonging to some Rn, and y could just belong to R. Okay. It doesn't have to. Y could also be a vector, but let's take the case where y is a scalar. So your goal is to find the vector A, which is an n-dimensional vector, and the scalar B, so as to minimize the error in your fit. So the error is measured. So think of, I'm basically in this one-dimensional example, where X is one-dimensional. We have trying to fit a line that best fits these points. And the error for this point is basically the difference between the line and the point, the value of y for the point and the value of y on the line. Okay, and so we can form what's called the residual sum of squares. So that's one way to do it, to measure error. So the error can be, you can sum up over all the data points. So yi minus A transpose xi plus bi. And then you take the square of that. This is a residual sum of squares, so basically it's the squared error. And the optimization problem becomes finding the A and the B to minimize this RSS. Sorry. RSS. Okay. We'll talk about optimization algorithms later that will allow us to do this minimization effectively. Okay, practical algorithms to do this. Okay. Another application, also in the context of machine learning, because it's actually one of the most interesting applications, modern applications of optimization, right, in the context of learning. So you, for example, we want to do binary classification. So you have a bunch of data points. In this case, the data points are marked orange here and blue here, or purple, I guess. Okay, and you want to find a boundary that separates these so-called training data points. Okay, and if you can find a good boundary that separates these training data points, then maybe you can use that boundary to classify a new point as either orange or blue. Okay, so that's the idea behind supervised learning, supervised classification. So basically the goal here is to learn, in some sense, the best boundary, and best really depends on how you define the problem. Okay, so there's some best boundary. To separate the classes. Okay, and we'll talk about two specific examples a little bit later in the course. One is support vector machines. And the other is neural networks. And both of these methods to find the boundary can be posed as optimization problems that need to be solved. Okay. it's a little messy to actually write down the optimization problems. So that's why I've not done it here, unlike how we did it for this example up here for the linear least squares. Okay. All right, so now let's talk about another application. This is a slightly different type of problem. This is internet resource allocation. Again, this could be also resource allocation in other networking contexts. Okay, but here's the idea. So you are trying to send information along various routes in the internet. Now, the links between two of these nodes in the network have certain capacities associated with them. Okay, the capacity of a link is how fast it can carry information. So the capacity of link L is called CL in bits per second. Now, a route is formed by basically going from some source to some destination through various links in the network, right? And if a link L belongs to R, we say that L belongs to R if link L belongs to route R. Okay, and there's a data rate for files that are carried on a certain route. Okay, so that's the data rate on which you can carry, based on the link capacities. There's a data rate at which we can carry links files on route R, and based on the data rate at which you carry those files, you get a certain utility. For example, if you're watching streaming video, okay, if you get a higher data rate, you get a higher quality video. Okay, so your utility will be higher, right? All right. So the optimization problem is to maximize the sum total utility across all routes. So, okay, but there are constraints, because if I look at XR, so every link that's used in a route, okay, if link L is used in the route, okay, it can only accommodate a certain maximum capacity. So if I look at all routes that use a link, okay, so R such that L belongs to R, all of those, if I sum up the data rate, what should be the upper limit for that?
CL,
Yeah.
the capacity?
The capacity, yeah, so CL. So that's a constraint. And of course, the XRs, all the data rates have to be positive, non-negative for each route. Okay, so the optimization problem is to maximize the utility under those constraints. And so this is called a constrained optimization problem. Okay, and these are called inequality constraints. Okay, and we'll study how to solve these kinds of problems, specifically in the second third of the course, roughly. Here's another constrained optimization problem. This is a power allocation problem in a wireless network. So you have a transmitter, and you have the option of sending the information from the transmitter to the receiver on M parallel channels. Okay, but each of these channels has a different kind of noise level associated with it. So if I say use different frequency bands, some frequency bands may have less noise than others. Okay, so I want to allocate. If I transmit on a certain channel, the rate that I get on that channel, okay, is roughly, this is actually based on what's called Shannon's capacity formula, but you don't need to worry about that. The rate that I get on the channel I can be roughly log of 1 plus the signal to noise ratio, right? And the signal to noise ratio is the power that I use to transmit on that channel, and the signal power essentially, and then Ni is the noise power, right? So 1 plus the signal to noise ratio is the rate at which I can transmit on the channel. So what I want to do is allocate power across different channels so that I maximize my my overall rate. Okay, so the problem here is maximization of such that summation subtotal power is less than the power that I have to use, and each of those powers has to be non-negative. Okay, this is another constraint optimization problem, right? And we'll see how we can solve such problems a little bit later in the course. Okay. All right. All right, so now let's start with some material that's a little more formal, optimization, getting to the core of optimization now. Let's look at conditions for optimality, right? All right. So first let's look at some definitions, right? So you want to minimize over some set S, or maximize over that set S, some function. Okay, and this course mostly will be dealing with just real valued. That means f maps some n-dimensional vector to the real line. So it's a real valued objective function. And S is called a constraint set. And we saw an example of that on just the previous page. So here's this is my, in this example that we saw, this is my function f, which is the sum of the utilities. And the constraint set is defined by these inequalities. So these are I'm maximizing over the xr's, and the xr's have to satisfy these constraints. Okay. So that'll be the typical form in which an optimization problem will appear in this course. So you have a real valued objective function, and I have a subset of Rn, which defines my constraints. Okay. Now on that constraint set, x star is said to be a global minimum if f at x star is less than or equal to f of x for all x belonging to S. Okay, obvious definition, right? A global minimum if it's smaller than any other value that f can take, smaller than or equal to. Okay, now this global minimum is going to be unique if what other condition holds. It's going to be unique if I look at f of x star, if this is strictly less than f of x for all x not equal to x star, then this is the only one that can be the global minimum, right? Because it's strictly less than every other x. Okay. Now, we'll also define something called a local minimum. Local minimum definition is a little more complicated. Here, what we're saying is that if we just look around the region, then in some ball, basically, I can actually find a little ball around x star, sorry, such that within that ball, x star corresponds to the smallest value that f can take. So x is called a local minimum if there exists an epsilon such that epsilon positive, such that f of x star is less than f of x. But this is not for all x belonging to S, but for x such that x minus x star is less than epsilon. So I'm just looking at this epsilon ball, right? And within that epsilon ball, f of x star is smaller than f of x. Okay, so those are the definitions for a global minimum, local minimum, and unique local minimum. The inequalities are, by the way, can you have a unique local minimum? It doesn't even make sense. Well, if there was only one local minimum to the function, right? Then that local minimum will also be the global minimum, if it's unique. Right? So there's no point in defining something called a unique local minimum. Or you can have uniqueness of the local minimum within this ball if you want. So that might make some sense in some context. So these inequalities are reversed for the maximum, right? That's all. So mostly, when we talk about optimization, we talk about minimization in this course, with the understanding that so maximizing a function is the same as minimizing the negative of that function. So we'll only look at minimization problems. Now, all global minima are local minima, but not all local minima are going to be global, of course. You could have multiple local minima that all correspond to the smallest value that f can take. So you could have multiple local minima that equal the global minima. Okay, but not all local minima have to be global minima. Right? That makes sense. All right, here's a picture, a simple 1D picture. So in this picture, the y-axis is my function, x-axis is just x, and here's a local minimum. Okay, here's a local maximum, and this is a global minimum. So basically, my set S could be this set here on this set here. This is my set S. Okay, I'm just looking at that window of my x-axis, and that's my set S. Over that set S, I have a local minimum here, local maximum we just pointed out, and then this guy will be the global max, and this is the global min. Okay. Any questions?
The endpoints, are they also locals?
Yeah, so we'll actually talk about that in a little more detail later. So what about these endpoints actually? So this endpoint is actually a local max. Okay, assuming that again the set is closed. If the set is closed and I include this left-hand point and the right-hand point, and this would be a local min. Okay, and we'll actually talk about necessary and sufficient conditions maybe in the next class. I didn't intend to cover any more material in this class. But let's actually talk a little bit about that since we had a question about the endpoints being local minima and maxima. Set. So just by looking at this picture, you can immediately see, and you probably saw this in the calculus course before, that these local minima and maxima satisfy a property. And what is that property in one dimension?
The derivative is 0.
The derivative is 0. Very good. So at these extreme points, the derivative is 0. But that seems to only hold for the points inside, right? Right. What about here? I mean, here the derivative is not 0. Here it's some negative value. And here also it's some negative value there. So it's not necessarily it's not necessarily 0 if you have a constraint set like this. Okay? So you could have extreme points at which the derivative is not 0, but they can correspond to local min or local max, or even global minima, right? It could happen. For example, if this function were to go up there like that, and you know, that could be a global maximum that happens at the endpoint. Okay, but so more generally, we'll see that if we didn't have any constraints, so if we allowed this S to go all the way to minus infinity and plus infinity on the right hand side, if we don't constrain things, then it's true that these extreme points correspond to the extreme points will only always correspond to the derivative being 0. Okay. All right. But what's the generalization of that idea in higher dimensions? Okay. So in higher dimensions, the analog of the derivative being 0 is that the gradient of the function is 0. And what's the gradient of the function? So maybe I'll just create a new page. So what you might remember this, you know, from your multidimensional calculus class. So the gradient of a function of where if x is a vector is actually a vector, and what are the components of that vector?
Partial derivatives in each.
Partial derivatives of f with respect to each of the components, right? So you put them all together into a vector. Okay, and you can make the column vector if you want. So this is the gradient of the function, and we'll see that, and we'll talk about necessary conditions for maxima and minima in the next class. And we see that basically a necessary condition for unconstrained optimization, where you don't have this set S, or you're basically considering the entire Euclidean space Rn. If you do that, then a necessary condition for having an extreme point is that, or having a local minimum or maximum, is that the gradient has to be 0. Okay. There's another quantity which will play a role as well, and we know something about that from your undergraduate calculus class. So what property does this minimum have? If so, the gradient, this local, or actually in this case a global minimum. But what property does this have? So this we see that the gradient is 0, but what other property does it have in terms of derivatives?
It's convex.
Yeah, so it's locally convex. So what's that in terms of as a derivative condition?
Second derivative is positive.
Second derivative is positive. Very good. So second derivative is positive here, right? And second derivative is negative for a local max. So, but so there is actually an equivalent condition in n dimensions, and that's actually based on a matrix, and which is why matrices are very important for this course, right? So you look at what's called the Hessian of the matrix, okay, and this is called the Hessian. So this is the gradient. It's called the Hessian. So the Hessian of the matrix actually has is a matrix that has all the second derivatives in it, right? So it's basically del f del x1 x1, x2 here, and the x1, sorry, this should be not x1, x2. This x1 squared, this is x1, x2, and so on. And then, and so on. So all the diagonal elements are the partial second derivatives, and the off-diagonal elements are the cross derivatives, right? So basically, if I look at the ijth element of this matrix, is del squared, not del f squared, but del squared. That's the notation. Del squared f divided by del xi del xj. Okay, so this is called the Hessian, and what do you think is the equivalent condition for the Hessian being the second derivative being positive, but in higher dimensions, what does that condition translate to?
Positive semi-definite.
Positive definite.
Yeah, positive definite or positive semi-definite. So those are the kinds of conditions that will characterize a local minimum or a local maximum. Okay, and positive definiteness for local minima and positive negative definiteness for maxima. Okay, so we'll talk about that, those kinds of conditions in the next class. But before that class, before next Tuesday, if you it'll be good for you to just review some of your basic knowledge of gradients and Hessians, which you should have seen in a previous course. Okay, we'll of course we'll I'll give you enough information here so that this course is self-contained, but it'll be good for you to be at least familiar with your prior knowledge of this material, so that you'll be comfortable with the material here. Okay, so I think we're almost out of time. People have any questions?
So I have a question from the previous slide. I guess we're going to talk about it.
Yeah.
So if you go down, so if there is no inherent ordering to the set that X belongs to, then how does it change the optimization problem? So here you could draw an x-axis with some ordering of the S.
Yeah, so we have to impose some conditions on S. Okay, for example, we'll see that if S is convex, and we'll define what we mean by that in the next class if you haven't seen it before. So if S is convex and closed, then there are there's a way to do the optimization problem of S. Again, constraint optimization is going to be more complicated than unconstrained optimization. Okay, the other way to define S might be through inequalities, and we saw that in the examples. Okay, so in these examples here, this defines a constraint set, or here this defines a constraint set. So in fact, you could have inequality constraints that are inequality constraints that don't correspond to a convex constraint set, but you can still have efficient ways to solve those problems. Okay, but again, in the first 8 or 10 lectures of this course, we'll be mostly concerned with unconstrained optimization. Okay, and then we'll complicate things as we go along in the second third of the course. Does that answer your question?
Yeah, thanks.
Okay, well, there's some chats.
I have a question.
Yeah, okay, I think I answered all of those questions. Okay.
I have a quick question.
Yeah.
Can you clarify what a leading principal minor is and how that?
Oh, so leading, basically you keep the first k rows and first k columns in the matrix.
So So you keep getting bigger, like K
Yeah,
spaces once you run?
basically go down the diagonal. That's why it's called, leading, and those are called the leading principal minors. Whereas if you include the other minors, then they're other principal minors, then you could, for example, this could be, by the way, what's an example of something that's not a principal minor? Here, so basically, so the leading principal minors of this matrix are this, and this. But if you include other minors, okay, you could have this be a minor and this be a minor, and then you could remove this part and get another minor, right? So the principal minors are obtained by removing any k rows and the corresponding the columns of the same index, basically. Okay, but if you look at minors, you could take off, say, you could take off the first column and the second row. Okay, and then you form a minor there. That's not a principal minor. Okay, and minors are useful in defining what's called the adjoint of the matrix, right? So, and you might have seen that in the context of computing the inverse of matrix. Okay, does that answer your question?
Yes. Thanks.
All right, so yeah, do provide any feedback on the TA office hour times from 5 to 6 in the evening. We could make it later if that's more convenient for people in China and India, so just let me know. We can try 6 to 7, for example. Okay, but 6 to 7 may be too late for the student who's joining from Turkey, I think. I don't know if he's there right now. He might have already signed out. Okay. All right. Okay, so talk to you guys next week.